Hello, friends, and welcome to our first lecture in Unit 3, which is all about chemical equilibrium. In this lesson particularly, we are going to focus on reversible reactions and the equilibrium constant. So almost all reactions are reversible. The majority of reactions are reversible. What does reversible mean? They can go in the forward direction or the reverse direction. I say almost all. We talked about this in class. You can't unburn something. You can't unexplode something. But the majority of reactions are what we call reversible. So they can go in the forward and the reverse. It means that reactants can collide to form products, and then products can collide to form reactants, and so on and so forth, back and forth. And eventually we're going to get to a place where there's no net change. So we see that right here. The concentration of my product is remaining the same, and the concentration of my reactant is remaining the same. So there's no net change. If we look at the rate, the forward reaction is decreasing, the reverse reaction is increasing till we get to a place where they are equal. So we call this state equilibrium. So equilibrium means that the rate of the forward reaction equals the rate of the reverse reaction, and the concentrations are remaining unchanged. So those are the two things that characterize a system at equilibrium. Something important to keep in mind is that equilibrium is a dynamic process. Molecules never stop moving. Atoms, particles, they're constantly in motion. So even though we have no net change, that does not mean reactants aren't turning into products and products aren't turning into reactants. Okay, the numbers remain constant, but they are shifting back and forth at all times. So if you remember in the video, if we're zooming in to one set of a face arm dude and an armless person, they can collide together and swap that appendage, and then they can go back. But if I zoom all the way out from like super high up, we would just see the numbers staying constant, okay? But I don't want you to think that that means that nothing's moving or nothing's changing. It just means there's no net overall change. Chemical equilibrium can also be established from either direction, meaning I could start with all reactants form from product before I then establish equilibrium, or I could start with all product and start forming reactant until I reach equilibrium, or I could have a mixture of both of them. All systems that are reversible reactions will eventually reach equilibrium. That's why we sometimes refer to it as like nirvana. So they're all going to reach equilibrium at some point, and they can do it from all reactants, they can do it from all products, or they can do it from a mixture of both. This also can happen for physical changes as well as chemical reactions. So physical changing, meaning changing state. So for example, in regular chemistry, you would have looked at these. These are a phase diagram. We will go over these in more detail later this year. But I like to point it out because anywhere along this line, if you are perfectly at, for example, this specific pressure and temperature, you are in perfect equilibrium between gas and water. If you think about a phase diagram or a heating cooling curve from solid to liquid, anywhere along this line, we're in equilibrium between the solid state and the liquid state. So all equilibrium equations have what's called an equilibrium constant. It is also a K, but it's really important that you notice that it is a capital K rate constant was a little lowercase k. So all equilibrium constants are capital K. Equilibrium constant is constant at a given temperature. So again, it is temperature dependent, but as long as the temperature stays the same, the constant stays the same. It's also unitless. There is no unit for the equilibrium constant. So if we're given this generic equation right here, so the lowercase letters being my coefficients, the uppercase letters being my substances, the equilibrium expression is always going to be products over reactants, and we're going to raise them to their coefficients. We have two ways of expressing this generic equilibrium constant. We can express it in terms of concentrations, in which case it is technically called Kc, or we can write it in terms of partial pressure, in which case we write it as Kp. Concentrations could be for aqueous or gases. Partial pressure is only used for gases. Now, in just a minute, I'll go over why I only used aqueous or gas and I didn't use any other state. Okay, but here we see for Kc, we use brackets to indicate concentration. We put our substance inside the bracket, and then we put our coefficient to the top right. If we use partial pressure, we typically use a capital P to indicate that we're using pressure. We use parentheses because it's not concentration, so we don't need those brackets. And then we put the substance below the large P, and then we raise it to its coefficient. So we'll write some of these with actual substances, and you'll see what I mean. But those are the two generic expressions for the equilibrium constant, either in terms of concentration or in terms of partial pressure. So speaking of partial pressure, what do we mean by that? So something that you need to remember from regular chemistry is Dalton's law of partial pressure. Now, all it states is something that seems kind of obvious after you know that it's true, but if I want to know the total pressure of a mixture of gases that are inert, meaning they don't react with one another, so I combine them together and now we have two gases but they're not reacting, then the total pressure is simply equal to the partial pressures added together. So that's nothing complicated. I tell you this for two reasons. One, to explain why we can use partial pressures to calculate the equilibrium constant. And two, just in case you're ever given a problem where maybe you're told the total pressure and you're told one of the two partial pressures, well then you could just subtract to get the other partial pressure. So the total pressure for a system of gases is just equal to the individual partial pressures added together. Okay, so let's do an example. If I'm given this equation right here, dinitrogen tetroxide decomposes into two nitrogen dioxides. If I wrote the equilibrium constant expression in terms of Kc, in terms of concentration, then I use brackets and put product raised to its coefficient over reactant raised to its coefficient, which is 1, so I just don't have anything there. If I write it in terms of pressure, again, I use parentheses and I use a capital P to indicate partial pressure, and I put the substance kind of as like a subscript down below, and then again, I raise it to its coefficient. So that's how we write a generic equilibrium expression. So if you're asked to write an equilibrium expression, you do not have to know what the actual concentrations are. You just plug in the substances and their coefficients. Now, something to point out in these two examples, this first one, you'll notice that I am missing the solid sulfur. It doesn't show up here. And that's because solids do not appear in equilibrium expressions. because a solid cannot have a concentration and it cannot have a partial pressure. So there's no way to report the concentration or the partial pressure of a solid, and it can't change. You can't change the concentration of a solid. It's a solid. And so they do not appear in equilibrium expressions. Same thing for this example over here. We have ammonia plus water making ammonium and hydroxide. You will notice I am missing the H2O. It is nowhere in my denominator. And that's because liquids do not appear in the equilibrium expression, because you can't have a pressure, a partial pressure for a liquid, a pure liquid, and you can't have a concentration or a partial pressure of a pure liquid. The only thing that we can have partial pressures of or concentrations of are aqueous and gas. So just to reiterate, only aqueous and gas in our equilibrium constant expressions. Okay, so very, very important. Do not ever include solids or liquids. Okay, so let's do some practice. Really simple. Just go ahead and pause the video if you would like, and then come back to it and see the answers for the equilibrium expressions. So this tells me to do it in terms of Kc. So Kc equals products over reactants, so O3 squared over O2 cubed. I use my brackets because I'm doing concentration. Same thing here, product in H3 squared, because it's coefficient of 2, into H2 to the third, because it's a coefficient of 3. And last but not least, Kc equals my product, H2O to the 6th, NO2 to the 4th, divided by NH3 to the 4th, O2 to the 7th. So for all of these, I just did products over reactants raised to their coefficient. All 3 of these reactions had nothing but gases, so there was nothing I had to leave out. I could include all products, all reactants. This time it asked me to write the equilibrium expression in terms of Kp, so in terms of partial pressure. So the only thing I'm going to change is just that I'm going to write Kp, and instead of using brackets, I'm going to use the capital P, and I use parentheses just to keep the subscript kind of outside of it. The products over reactants raised to their coefficients. All of those were gases, so all of them can be included. Now for the second one, my product is a pure liquid. I cannot include it in my equilibrium expression. It's my only product! What do I do? What do I put in a fraction if I don't have a numerator? 1. So if ever this happens and your product is a liquid or a solid, and there's no product as part of your equilibrium expression, you're just going to do 1 over. And now we'll put our reactant. So the pressure of P4 and the pressure of Cl2 to the 6th. So if ever that happens, you just do a 1. If ever you don't have a reactant to put because it's a liquid or a solid, then you would only have your numerator, you would have no denominators. Technically it's 1, but anything divided by 1 is itself, so we just leave it off. Okay, what the heck do these K values mean? What does it even matter? All right, it tells us kind of the relative composition of a system at equilibrium. How much product is there? How much reactant is there? So I'm going to remind you that K, P or KC, is always products over reactants. So if my products are much bigger than my reactants, then K is going to be much greater than 1. So what we call that is product favored. So if a reaction is product favored, its K value is much bigger than 1, and it means that once equilibrium is established, I have more product than I have reactant. So that's this example right here. Now let's say this time, now my reactants are way bigger. I have more reactant than I have product. We call that reactant favored. And that's going to make that if a denominator of a fraction is bigger, it's going to be less than 1, typically a lot less than 1. Okay, and so in that example, when we reach equilibrium, my concentration of my reactants is way more than my product. There's still reactant and product there, but the reactant is just in a much higher concentration. Now, every so often, we will have a time where the concentration of reactant and concentration of product is about the same. That would give me a value of almost 1. And if that happens, then the reactant and product concentrations are pretty much equal once the system establishes equilibrium. Now, it's really important to understand that K is at equilibrium. It is not at the beginning of the reaction. It only refers to once equilibrium has been established. So let's say we start a reaction and we only have reactants. Well, of course there's more reactant than product, but we're not at equilibrium yet. We have to wait for the system to get to equilibrium, and then we could see, is there more products or is there more reactants? So let's practice interpreting a K value. So for this equation, solid sulfur reacting with oxygen gas to create sulfur dioxide, we are given a K value at 25 degrees Celsius. We're simply told that because, remember, Ks are only constant at constant temperature. We're given a value of 4.2 times 10 to the 52nd. That's huge. What that means then is once equilibrium has been established, the concentration of SO2 is much greater than the concentration of the reactants. Well, and then S doesn't have a concentration, but that also means then that we call this product favored. All right, let's look at this one. We have silver chloride dissociating or dissolving into silver ions and chlorine ions. And I'm given a K value at 25 degrees Celsius, 1.8 times 10 to the negative 10. Now that's a really small value. That's much less than 1. And if that's the case, then that means that my reactant is greater than my product, or I am reactant favored. So we've talked about how Kc is the equilibrium constant written based on concentrations, and Kp is written based on partial pressures. Now there is a mathematical expression that relates both of them and allows us to convert from one to the other. Kp is equal to Kc times the ideal gas constant, the temperature in Kelvin, raised to the delta N. Now delta N is the difference in the sum of the coefficients of gas in the products minus the number of coefficients of gas in the reactants. So an easier way to say this is delta N equals the number of gas molecules in the product minus the number of gas molecules in reactants, okay? Now, if you'll notice up here, I told you this is not given on your reference sheet. So what does that mean? It means that you will never actually have to plug numbers in to this equation. The only time that you will be asked to quote unquote convert between Kp and Kc is if you have a reaction like this, where the number of gas particles in the products equals the number of gas particles in the reactants. Why? What does that mean? Well, if we look at our equation, if they are the same, then we get that delta N is 0. Well, then this raised to the 0 equals 1, so that is removed from my expression, so Kp equals Kc. So if you are ever asked what is Kp or what is Kc when calculating the other one, you should look and see that there's the same number of gas molecules in the reactants as there are in the products. So if Kc for this equation also equals Kp, and your justification would just be the same number of gas molecules. So if ever you're asked to find Kp or Kc and then calculate the other one based on it, it should be equal, and you will say because there's the same number of gas molecules on the left and right. However, if I didn't show you this equation, it would make absolutely no sense why Kp equals Kc when there's the same number of gas molecules on the products as there are in the reactants. So that's why I show you the equation, but you will not have to plug things in for it. Okay, kind of the last concept for this lesson. If we are given a reaction and then we're giving it its equilibrium constant, I might then be able to use that reaction and its equilibrium constant to calculate the equilibrium constant of a different reaction. And so we have a few rules that tell us how to do that. The first is the coefficient rule. So if in order to go from one reaction to another to kind of change one reaction to a different reaction, if I have to multiply through by a certain coefficient, then I take that original reaction's K value and I raise it to the coefficient. So my new K value would be the old K value raised to the coefficient. So to give you an example of what I mean by that, I want to know what is the K value for 2 iodine plus 2 chlorine making 4 iodine chlorides. I'm given this reaction and told its K value. Well, if I compare these two reactions to one another, I see that if I multiply this whole reaction by 4, then this becomes 2, 2, and 4, which matches my reaction that I'm trying to calculate K for. So then the K for this reaction is equal to the old K raised to the 4, because I multiplied through by 4, so I raise its K value to 4. And I get 4.25 times 10 to the 10. So I used this K value in this reaction to calculate this K value for this reaction. Another thing that could happen is I might just have to reverse a reaction. That's the reciprocal rule. So if I reverse a reaction, I take the inverse of its equilibrium constant. So the new equilibrium constant is going to be 1 over the old one. For example, if I'm trying to find the equilibrium constant for this reaction, given this reaction and this K value, well, I hope it's easy to see that this reaction is just the reverse of this reaction. If I flip it, now I have the reaction I'm looking for. So then my new K value is just 1 over the old K value, which equals 4.72. Oops. And I'll remind you that K is unitless, so that's why I don't have any units here. The last rule is we might be able to combine some reactions together with their K values to find my new reaction. If that's the case, this is the multiple equilibria rule. So if I add reactions together, think about a mechanism's elementary steps, right, being added together for the overall reaction. If I can add reactions together to get a new reaction, then the new K value is equal to the other K values multiplied together. So if this is the overall reaction I want to know my K value for. Well, now if I look at these two reactions, I want to know how can I manipulate them? Do I need to reverse them? Do I need to do anything? Or do they just add up to the overall reaction? Well, in this case, N2 cancels out and O2 cancels out. So I'm left with 2NO plus Br2 yields 2NOBr, which matches my original equation. So I didn't have to do anything but add them together. So then my new K value is equal to each of the individual K values multiplied together. Oops. 2 times 10 to the negative 27 equals 2 times 10 to the third. So because this reaction and this reaction added together to make my overall reaction, then I multiplied these K values together to get my new K value. So what if I have to do multiple of these rules at the same time? No problem. Here's my overall reaction. Hydrogen plus carbon dioxide is in equilibrium with carbon monoxide and water. Now somehow these two reactions together need to add up to the overall reaction. What I typically do is I look to see if there's a reactant or a product in the wrong spot, okay? Well, if I look here, H2 is a reactant, and it's a reactant in my overall, so that's good. H2O is a product, and it's a product in my overall. But if I look at the second equation, I have carbon monoxide in a reactant, but it's a product here. So what I'm going to do is I'm going to reverse this reaction. I'm going to write it in the other direction. And when I do that, I know that I take the reciprocal. So it's 1 over 490. So sometimes what I even do is I even cross the original out so that I don't use it. Now, when I combine these two reactions, cobalt cancels, cobalt oxide cancels, I'm left with H2 plus CO2 yields H2O plus carbon monoxide, which is my overall reaction. So then my new K value is equal to the original K values, and I'll rewrite this, times 1 over 490. So I just did both rules. I reversed one of them, and then I had to add them together, so I multiplied their K values. All right, so here's another example. What is the K value for this reaction given this information? Well, I can easily see first that this new reaction is this old reaction reversed. So I'm going to rewrite it in the reverse direction. And I know that that means my new K value is the inverse. Now these are still not the same because my coefficient for NH3 here is 2 and here it's 1. Here it's 1 and here it's 1/2. Here it's 3, here it's 3/2. So clearly I need to multiply through by 1/2. So then that means for my K value, I raise it to the 1/2. So my K for this reaction is 1 over 1.3 times 10 to the negative 2, all of it raised to the 1/2. And when I do that, I get 8.77. Okay, here's our last example of manipulating K, and this one's going to be our most difficult. We're going to have to do multiple things here. Okay, so this is the overall reaction I am trying to calculate the K for. And I'm given these three equations, in their equilibrium constants in order to do so. So again, I told you my method is to typically first look for products or reactants that are out of place. So in this reaction, N2O, dinitrogen monoxide, is a reactant. Well, down here, it's a product, and so that can't be the case. So I'm going to rewrite this first equation reverse. 2N2O, 2N2 plus O2. And then that means the new Kc value is 1 over 1.2 times 10 to the negative 35. Okay, so now I have my N2O is in the right place. Now here N2O4 is a product. Well, N2O4 is a reactant here. So I'm going to also reverse equation number 2. Which means that I'm going to do the reciprocal of the K value. So the last one, I have 1F N2 plus O2 creates NO2. Well, O2 is a reactant here, and it's a reactant here, so I'm not going to flip this third one. So what I'm going to do is I'm going to mark these first two out because now here are my 3 equations that I'm using. Now let's see if they add up. Well, here I have 2 N2O4s, but here I only have 1. Well, that's not going to work. So I'm going to multiply this through by 2. When I multiply through by 2, I now have 4 and 2. So then I have to raise this to the second. Now 2 N2Os, 2 N2s, and 1 O2. Here I have half of an N2 and I have 1 NO2. Well, NO2 is not part of my overall reaction, so I need to get rid of these NO2s. So I'm going to multiply this by 4. That also makes sense because when I do that, the coefficient for N2 becomes 2, and I need those N2s to cancel as well. So now I have 4 oxygens, 4 NO2s. Now, because I multiplied through by 4, I have to raise this K value to the 4th. All right, now let's see if I finally have it to where my reactions add up. So I have 2 N2s as a reactant, I have 2 N2s as a product. So I'm going to cancel those out. I have 4 O2s as a reactant, but only 1 over here is a product. So that means that 1 of these cancel out, and my coefficient is now a 3. I have 2 N2Os. They don't show up anywhere else, so that doesn't cancel. I have 4 NO2s, 4 NO2s, and so that cancels. And so I am left with 2 N2O plus, what's my other reactant? 3O2 in equilibrium with 2 N2O4. Whew, that finally adds up. So then I have to multiply all these together. So my new K value is 4.1 times 10 to the negative 9 raised to the 4th times 1 over 1.2 times 10 to the negative 35 times 1 over 4.6 times 10 to the negative 3. When you raise to the second, because I had to raise to the second. So when I do all of that math, I get 1.1 times 10 to the 6th. So I would say try that on your own. Make sure you can plug it into the calculator and get this K value. All right, guys, that's it for lesson 1. Thanks for listening, and I will see you next time.